Bạn nào vào lớp thì các bạn gõ họ và tên đầy đủ ở cái mục chat để mà điểm danh nhé. Trong lúc đợi các bạn lên đầy đủ, tương đối đầy đủ một chút thì chúng ta sẽ xem cái video dạy học số của môn học.
both compression and tensile strength. And compression and tensile strength almost the same. Here we have an example. The concrete B15 has the compressive strength about 8.5 megapascal, and for the steel A1, it has the tensile strength and compressive strength about 225 megapascal. However, steel is an expensive an expensive material. So because of the properties, concrete has a very good compressive strength, and reinforcement have good compress and tensile strength. So people come to the idea that reinforcement is put into concrete to create reinforced concrete structure. In particular, compressive stress subjected by concrete and steel, and the tensile stress is bear by steel to create reinforced concrete material with better bearing capacity and superiority. Reinforcement is placed in concrete not only for tensile strength but also for bending, twisting, cutting, compressing at the center and off center. When arranged the building loads reinforcement, the cross-sectional inside the structure cell weight will be reduced, while ensuring high strength to the structure. So here we have an example of bending reinforced concrete components. For example, here we have a single beam with a fixed ends and a roller, and here we have a vertical load, and this two vertical load P will create a moment, a bending moment, and it causes the beam bend like this, and the upper part of the beam we have the compressive stress, and in the lower part we have the tensile stress. So people will arrange the reinforcement in the lower part of the beam to resist the tensile stress. So what is the difference between the left model and the right model? For the left model, we have the reinforcement is not so much. However, in the second model, in the right model, we have the reinforcement is quite much, and this the left model is plastic destructive with less steel, and in the right model, which much or exists steel, we have the brittle destructive. So we have to calculate to determine the reasonable reinforcement and place the reasonable reinforcement in the area of tensile resistant concrete. That is the compressive reinforced concrete components. So we have two column model, and these two columns model bearing the combination of loads include moment and axial force. So if the moment is this, it will be the last eccentric compression column. If the moment is big, and the reinforcement to be calculated and arranged line in this section. However, if the axial force N is big, then we will have the case small eccentric compression column and the reinforcement. The reinforcement will be calculated and arranged in the perimeter evenly in the perimeters of the sections like this. So we have to calculate and place the reasonable reinforcement in the both areas, tension and compression, resistant concrete. So yes, question here. Why concrete and reinforcement in reinforced concrete can cooperate to bearing load? So here we have 4 reasons why concrete and reinforcement can work together to bearing the load. The first one is due to the adhesive force between concrete and reinforcement. The second one is there was no chemical reaction between concrete and reinforcement. The third one is concrete protect reinforcement against corrosion. And the final one, concrete and reinforcement have almost the same coefficient of thermal expansion. So here is the adhesive force between concrete and reinforcement. The adhesive force is equal to the cement grip force, and it takes about 25% plus the friction force about 75%. And here we have the ankle length. This is the reinforcement, and this is the concrete. And we have a tensile force and here, and we can calculate the stress diagram of the friction. So reinforced concrete can withstand loads due to the friction here between concrete and reinforcement. And we can calculate the ankle length. This is the ankle length. It's about 15 to 20 diameter. The diameter of the reinforcement. Here is the corrosion of steel in concrete. Usually, the reinforcement will be put inside the concrete. However, if the concrete appear the crack, for example, here we have the concrete appear the crack. So the moisture and the penetration of oxygen and chloride will go through the concrete and contact to the reinforcement surface, and it can penetrate through concrete and penetrate through glass and contact to the reinforcement and to create corrosive products. And when the corrosion happens here, the volume of the reinforcement is expanded and the cracking is widened. And the corrosion continue. Here is the example for the consequence of corrosion in the bridge here. So in design, we have to calculate to ensure the the thickness of the concrete, and reinforced concrete protection layer must be thick enough, and depending on the external environmental properties, and we must ensure and calculate the thickness of the concrete. And this is the reference you can see. The third part of the chapter 1 is the classification of reinforced concrete structures. So according to the construction methods, we will divide the reinforced concrete structure into 3 groups. The first group is monolithic reinforced concrete, then the precast reinforced concrete, and the semi-precast concrete reinforced concrete. And according to the mass, we can classify the reinforced concrete structure into heavy concrete, which the average density about 22 to 25 kilonewton per cubic meter. And for small grain concrete, we have the average density about 18 kilonewton per cubic meter. And for the large concrete, we have solid or hollow structure, and we have porous concrete and special concrete like cell stress concrete. And according to the stress test, we can divide the reinforced concrete structure into 2 groups: normal concrete and pre-stressed concrete. So this some figure, some pictures about the using the application of the monolithic reinforced concrete. For example, here we have the multi-story building or high-rise building. They use monolithic reinforced concrete. And here, for multi-story building, they have the precast reinforced concrete. And also here is the precast reinforced concrete are used in constructing the multi-story building. And here they use the precast reinforced concrete to construct the supermarket or the factory. So the precast reinforced concrete, that means they are manufactured in the factory and then transport to the construction site and they do the connection. They do the connection to form the final building. And here is the precast reinforced concrete for apartments. So we continue to learn the 4 parts of the chapter 1. Advantages and disadvantages of reinforced concrete structures. So the advantages of reinforced concrete is the use of local materials. For example, sand, stone, brick, gravel. And these materials are available and easy to find, easy to use. So this is an advantage point. And reinforced concrete have greater bearing capacity than stone and wood-type structure, especially resistant to large movement. And reinforced concrete material can withstand dynamic loads, including earthquakes and explosions, and it can sustainable over time with low maintenance costs. And it's difficult to catch fire, so it has good fire resistant capability, and depends on the shape. Reinforced concrete can create any shape according to architectural and aesthetic requirements. So those are the advantages of reinforced concrete. And here's the disadvantages of reinforced concrete structures. The first one is the great cell weight. That means the reinforced concrete structure cell weight is very heavy, about 1,800 to 2,500 kilogram over cubic meter. So it is difficult to make a structure with a long span. It's very difficult. So we have to think about the solution. The solution for this disadvantages is to use the lightweight concrete and pre-stressed concrete or thin shell structure to reduce the cell weight of the reinforced concrete structure. The second disadvantage of reinforced concrete structure is the poor soundproof and heat proof. So to avoid this disadvantage, we use porous reinforced concrete structure. And the third one is the complex construction work and long time. So to reduce the time for construction work, we use the precast reinforced concrete structure. Precast. The final disadvantages of reinforced concrete structure is easy to appear cracks, and the crack will cause the quality and aesthetic damage. So in that case, we will use the pre-stressed structure, or we calculated the limit set to limit the width of the cracks and the length of the cracks, and we use the fiber reinforcement. And here's the summary table for the advantages and the disadvantages, and this is the solution for each disadvantages. So you can list by yourself and try to understand. The fifth part of the chapter 1 is the application fields and development strengths. There are many application fields of reinforced concrete structure. For example, we can see in civil and industrial engineering, or road, bridge and transportation, or irrigation, and even in special engineering like defense structure or nuclear power plant. For the development strengths, we have many research, like the research on new concrete materials, and they do the research on extremely high strength concrete with the strength bigger than 80 megapascal, or the bending concrete is another research strength. And there are many modern laboratory equipment with special sensor or large scale structural laboratory to do the experiments. And we develop new method on analysis and calculation of internal forces and design of reinforced concrete structures. So here we have many development trends for the reinforced concrete structure. And here we have many application fields for the reinforced concrete structure. For example, in civil and industrial engineering, this is an application field. We use the reinforced concrete structure for civil and industrial engineering. For example, here is a high-rise building in Ohio State in the United States. And for another example, we have the Opera Sydney. The Opera Sydney in Australia is also constructed by reinforced concrete, and it has the length about 183 meters and the width about 120 meters, and the area is about 1.8. And for the assembly hall of the Illinois University in the United States is also constructed by reinforced concrete. And here's the example for high-rise building, Water Tower Place in Chicago, USA. And this building had the height 262 meters with the 74 stories. And this is the TV tower in Toronto, Canada, with the height 553 meters, and it's also been constructed by reinforced concrete. And here is the Petronas Tower in Kuala Lumpur, Malaysia. It was built in 1992 and completed in 1998. With the height of 452 meters with 88 floors. And here's another high-rise building in the Shanghai, China. And even the Dubai Tower also has some parts of structure that's built from the reinforced concrete structure. And this is the Hoover Dam in the United States. It's very long and big dam with the length about 379 meters, and the height is about 221 meters, and the thickness vary from 14 meters to 183 meters, and the total volume of concrete is about 2.5 billion meter cubic with me. This is another example of the application of reinforced concrete. And in Vietnam, this an example of the using reinforced concrete. So you can see many example for the application fields. And this is the tunnel in Japan, Seakan Tunnel in Japan, and it connects to Iceland of Japan. So it's very long, about 53 kilometers. And this is the channel through the Manche Channel. And it connects the France and the United Kingdom. And this tunnel also built from the reinforced concrete. And here's the example for the researching reinforced concrete. For example, here's the bending concrete. Bending concrete. You can see here is the concrete plate which have the capacity of bending. And here's the example for large-scale structure testing. And here they are testing a column with the height about 3 meters and cross-section size about 100 and 350 millimeters. And this is the experiments with the many sensors. Here is the strength design, and according to the old standard of concrete of Vietnam, and we use the linear elastic analysis to calculate the force concrete internal forces. And this for plastic design, we use plastic design analysis to calculate the reinforced concrete internal forces. And displacement-based design research developed from 1990 for seismic design of reinforced concrete structure. This is the force and this the displacement of the structure. And we can calculate the building damages directly related to the strength. So this is the end of the 1.5 of chapter 1. Hello everyone, it's me again. And now we continue to learn the 1.6 physical-mechanical properties of reinforced concrete. So in this 1.6 part of chapter 1, we have three subparts. 1.61 physical-mechanical properties of concrete. And the second one is physical-mechanical properties of reinforcement. And the third one, physical-mechanical properties of reinforced concrete structures. At first, we study physical-mechanical properties of concrete. The mechanical and physical property is the mechanical properties and the physical properties. And the concrete mechanical property is the water ratio of water and cement, and the cement time and the sand and gravel and mixture and construction methods and condition for maintenance. Beside that is the concrete intensity. Concrete intensity is the basic characteristics of concrete, and it was determined by compression test according to TCVN 311H 1993. And for the mechanical properties of the concrete, we have two terms, strength and the strength. And for the physical properties, we have the following terms, shrinkage, grip, and waterproofing ability. At first, we will study the strength. In the strength, we continue to learn compressive strength, tensile strength, and the factors affecting the strength of concrete. For the strength, I will instruct you to know the strain due to load, strain due to shrinkage, and the strain due to temperature. And finally is the concrete elasticity modulus. First, we will study the strength. So what is the strength? The strength is the capacity, bearing load capacity of a material. So it depends on the stress test. We will divide into concrete compressive strength. The compressive strength of the test sample. Here we have the test sample. It's a cubic. And so the test sample is a cubic shape, manufacture and maintenance under standard conditions, and compressive testing at the age of 28 days, and the standard temperature is 20 Celsius degree, and with the humidity about 90%. So after making the experiment, we will have the results, and we can calculate the compressive durability level of concrete, and this so-called the basic quality of criteria. So we have the definition. The compressive durability level of concrete, and it was noted by the B letter, and it's the statistical average of the instant compressive strength in MPa with a guaranteed probability of not less than 95%, and it was determined on the standard size cubits. This is the size of the cubic sample. And this sample is fabricated and maintenance under standard condition and tested at age 28 days. So this is the formula to calculate the B value. And in this formula, the BM value is calculated by the statistical results. And M is the abbreviation for the medium. So this is the statistical average of the instant compressive strength. And here we have the new value. This is the new value. And new value is a coefficient of variation of the intensity of the standard test samples depend on the level of concrete production. And normally, the new value is equal to 0.135 with compressed concrete. And the BM is the statistical average of the compressive strength of the sample. And here we have the N1, N2, and so on to N. They are the numbers of standard test sample of the corresponding intensity B1, B2, and so on to Bn. And B is also known as the intensity compressive resistance. And this is the characteristics of the concrete for compressive durability. Next, we continue to learn the standard compressive strength of the concrete RBN. The standard compressive strength is the characteristic compressive strength B, and mentioning the behavior of concrete in reality is different from doing experiments. And this formula shows the relationship between RBN and B. This is the standard compressive strength. Beside, we have the calculated compressive strength of concrete, and this value is used in the calculation of the limited stage 1. And this the calculated compressive strength RB. And this the calculated compressive strength for the limited stage 2 RB SER. In these two formulas, the gamma BC is the reliability coefficient of concrete when compressing, and usually is equal to 1.3 to 1.5. For the gamma BI is the working coefficient of concrete, and it depends on the cases. So we finish the compressive strength. So remember, in the compressive strength of concrete, we have the two different groups: the standard compressive strength and the calculated compressive strength. In the calculated compressive strength, we have two smaller value. It's the compressive strength for the limited stage 1 and for the limited stage 2. So they are different. Be careful. Try avoid to misunderstand between these two values. Next, we go to the concrete tensile strength. Concrete tensile strength. The tensile strength of the test sample. And this here we have a test sample with the tensile force into different directions. So here we have the formula to calculate the tensile strength of the test sample, where NP is the sample for destructive force MT is the destructive force for the sample, and A is the sample cross-section area. So after taking the experiments here, we get the results of B1T, B2T, and so on to BNT. And we use the N1T sample number of sample for the B1T and other similar. We use the NNT number of sample for B and T. And we can calculate the tensile durability level of concrete by using these two formulas, where the new value as a coefficient of variation of the strength of the standard test samples and depends on the level of concrete production. And the new value, usually the new value is equal to 0.165 with the tensile concrete. And the BMT is the statistical average of the tensile strength of the test sample. And N1, N2, and so on, Nn are the numbers of standard test sample of corresponding strength are B1, B1T, B2T. T is the abbreviation for the tensile tension, and BNT. So next we consider the factors affecting the strength of concrete. The first factor affecting the strength of concrete is the ingredients and casting methods of concrete. They are the quality and quantity of cement, the hardness, the cleanliness, and the gradation of aggregate, and the water and cement ratio, the quality of concrete kneading and concrete compacting, and the maintenance condition. Next, we study the strength of concrete over time. So the strength of concrete over time is calculated by the formula of BG strain tip, with T is equal from 7 to 300 days. And here we have the chart. This chart shows the development of the concrete strength. As you can see here, when the time is less than 28, the concrete strength increased dramatically. However, after the 28 days, when the T number of days is small, the B time, the strength of concrete increase slowly, and asymptotic at a certain value. And when T is over 28 days, the strength increase but not significantly, and we can consider B 28 days is 100% intensity. At this point, you can consider this value is the 100% intensity. For the age of concrete, is the time from the time of making concrete. This is the first time, the first day we make the concrete, to the time being considered, and this is the age of the concrete. And we know the 28 days. And this law for your reference, concrete compressive strength. So to estimate the concrete compressive strength, we use many sample of experiments. For example, in Vietnam standards, we use this sample, this Q sample with the sign or the dimensions in millimeters. And we can also use other sample with this dimension. However, after finish the experiments, we have to use the coefficient of conversion to convert the value of this sample to the standard values. For the foreign standards, for example, the United States, USA standards, ACI 31H02, they use the sample. This is the standard sample for the ACI. And the values strength of this sample is equal to Vietnam standard multiply 1.2. So be careful when you use the foreign standards and Vietnamese standards. This is the sample for the ACI, and this is the sample for Vietnam standards. For the new Vietnamese concrete standards, this standards, we have many definition for the compressive strength and tensile strength. So your duty is to find this standard and read it at home. Here we have the computing or calculated value for the first limited state and the second limited state. And here is the flexural strength of concrete. So to estimate the flexural strength of concrete, this is the experiment, and this is the concrete sample with load P perpendicular to the concrete sample beam. And this load causes the moment, and it makes the concrete become flexural. And they can calculate the flexural strength of concrete. And next we study one term of the physical mechanical of concrete. This is the strength. For example, when we apply the load to the concrete sample, in the concrete sample we will have the stress, and this is the stress of the sigma is the concrete stress, and we have the epsilon value is the strain. So the stress and strain, they have the relationship, and here we have the chart to show the relationship between stress and strain of the concrete. At first, we consider the strain due to loads, and in A part, we study the strain due to the short-term effects. And here we conduct the concrete compression test and measure and establish the relationship between stress sigma and the strain epsilon. So here we have the D point, and the point D corresponds to the destructive sample. This is the destructive sample. And at that time, the stress of concrete was sigma CR, and the concrete strength is epsilon CR. And with the correct center cylinder patterns, we have the epsilon CR is equal to 0.002, and the bending components, for the bending components, epsilon CR can reach 0.0035 for the compressive edge. Consider the case when loading reach point A. Consider the case when the loading reach point A, not destructive, and then we reduce the loss. When we reduce the loss, the stress will decrease. You can see here, the stress will decrease in this part, and also the strain decrease. However, this part is not come back to the zero, but come back to this point. So the strain of the concrete has not completely recovered. It's only recover this part, epsilon EL. So the part which cannot be recovered when loading reach zero is called elastic strain. So epsilon PL is the elastic strain, and epsilon EL is the elastic. So you have to discriminate between the two values. This is the plastic strain, and this is the elastic strain. So the part which is not recoverable when the loading reach zero is called plastic strain. This plastic strain is epsilon PL. Remember it. So because the concrete also have the plastic strain and elastic strain, so concrete is an elastoplastic material. That means this material, concrete, have both elastic properties and plastic properties. And here we can calculate the concrete strain. So the total value of concrete strain is the epsilon B. This epsilon B is the total concrete strain and is equal to the summation of the elastic strain epsilon EL and the plastic strain epsilon PL. And we calculate the elastic coefficient nu is equal to the division of epsilon EL divide epsilon B, and normally this value is smaller than 1. And when the stretch is small, the strain is mainly elastic. When the stretch is small, you can see here, this part is a linear line. So when the stretch is small, the strain is mainly elastic. When we decrease the stress, the strain will recover and return to zero. So the strain is mainly elastic. However, when the stretch is large, it goes to the nonlinear part. Nonlinear part is the curved line, and the plastic strain increase, and the elastic coefficient decrease. To try to focus on my explanation and understand it. If you don't understand, you can raise any question here, and I will explain for you. Next is the another properties of concrete, mechanical properties of concrete is the grip. So what is the grip? When we apply a compressive test to point A and then keep him the load for a long time, we don't increase the load. That means the stress of concrete is a constant value, sigma B, but we keep it for a long time. The strain continues to increase to point B. When we keep it for a long time, the strain is not only epsilon B, but it's increased to the epsilon capital B. This normal B and this capital B. Increase to the point B. And the addition strain when the load does not increase is called grip. And this phenomena is, we call this phenomena when the stress is constant, but the strain continue to increase. This phenomena is so-called grip. So the concrete has the grip property. And here are some factors that affect the strength of the grip. When the stress increase, the strength of the grip increase. And for the large and water cement ratio, the strength of the grip. And for the small aggregate rigidity, the strength of the grip. And for concrete edge increase, the strength of the grip decrease. With the humidity of the environment decrease, the strength of the grip decrease. Next, we consider another physical-mechanical property of concrete is the shrinkage. And here we have the definitions. Shrinkage is a phenomena of reducing volume when concrete is hard in the air. And shrinkage phenomena is related to the physical-chemical change of cement hydration, to the loss of water energy due to evaporation. And shrinkage is an adverse phenomena. When shrinkage is obstructed or irregularly, there are cracks of ground space affecting the bearing load capacity of the structure. So it needs to be limited. And the factors affecting shrinkage are the larger of the surface, the more shrinkage it is, and the right environment shrink more than the moist environment. And shrinkage increase when more cement is used, and high performance cement and water cement ratio increase, and aggregates has porosity and fine sand admixture. So to limit the shrinkage phenomena, we can use some solution like keep moist regularly during the first period, or making expansion joints, or choose the appropriate concrete composition, compacting concrete, or reducing the water and cement ratio. The third properties of concrete is the strain due to temperature. It is also a type of deformation that appears during the using period of a building. When the temperature changes, the concrete shrinks, and the shrinkage depends on the heat expansion coefficient of concrete alpha T. And the solution for reducing thermal strain is utilizing heat loss. concrete elasticity modulus. So from this chart, we can estimate the concrete elasticity modulus. And here we have two different values. The first one is the initial elasticity modulus. Here, from the 0 point, the origin of the coordinate, we draw a tangent line of the curve, and this tangent have the angle with the strain axis, an angle alpha 0. And the initial elasticity modulus is EB. It's calculated by this tan alpha 0. And tan alpha 0 is calculated by the division of sigma B is the concrete stress over the elastic strain of the concrete. And this is the initial elastic modulus. And we have another value, is the elastoblastic modulus in strain modulus, or so-called name is the strain modulus. EB5 is equal to tan alpha. And tan alpha is the division of the concrete stress over the strain of the concrete. And we can estimate by the new value multiply EB, where U is the elastic coefficient. So we can see that EB5, the elastoplastic modulus, will vary when the load change. So here is an example experiment to estimate the concrete elasticity modulus. This is the estimation chart of EB, tan alpha and tan beta. And here's the old standards, TCVN 356. So in this old standard, we can see the mechanical indicators like standard axial compressions. This is the standard axial compression, and this standard axial tension, and this computing axial compression, and computing axial compression and elasticity modulus for the concrete with many strength grades of, for example, B15, B20, B25, B30, and this corresponding to the old standards. And this table is for heavy concrete hardening naturally. And the next slide, this one, is the physical mechanical indicators for the current standards. This is the new standard, TCVN 574. And it was published in the year 2018. So you can see it for reference. The second part of 1.6 is the physical mechanical properties of reinforcement. That means the properties of the steel. So in this part, we have smaller subpart. The first one is various types of steel. Next one is mechanical properties of steel, and the third one is classification of steel. First one, various types of steel. So for the steel or for the reinforcement, we have many types of steel, and based on the chemical composition and the method of manufacture, the steel mark is determined. Reinforcing steel in the reinforced concrete is usually low carbon steel or low alloy steel. commonly used carbon steels are CT3 and CT5 with the carbon ratios of 3 or 5 parts per thousand. And lower alloy steel has some more elements like manganese, silicon, and titan to increase the strength and improve some properties of steel. Reinforcement with the diameter bigger or equal to 10 millimeters is produced in bars and not exceeding the length of 13 meters. Usually, the length of a steel bar is only 11.7 meters, and reinforced steel is with the reinforced steel diameter smaller than 10 millimeters is produced in rolls, and reinforcing steel is produced by hot rolling methods with good ductility, often used in reinforced concrete. In addition to the cold work steel and hot work steels. In terms of forms for reinforcing concrete, with smooth reinforcement and bevel reinforcement, the bevel reinforcement will increase the ability to adhere to concrete. And there are also shape steel. In high-rise building. They are often used shape steel. Next, we consider stress and strain performance curve of mill steel and hard steel. We have the two curves, OABD and OAA1D1. For the curve OABCD, this curve represents the relationship of the stress and strain of the mill steel. And at elastic stage, OA is the elastic stage of the steel. You can see here is a straight line, linear line. The stress and strain ratio in the first order, and the line is a straight line. You can see OA is a straight line. So the relationship between the stress and strain in the elastic is a linear line. And through point A, the stress almost does not increase, but the strain still increase. And the line is the AB segment, and that's the yielding phase or bed of yielding, AB is the bed of yielding or yielding phase, and the stress corresponding to the yielding phase is the yield limit sigma y. So the stress here, the stress in the AB segment is the sigma y, the yielding stress. And passing the B point, the stress and strain increase together, but not increase according to the first order. That means this part is non-linear. And until the steel sample breaks at D point, the stress reach a durable limit, sigma CR, and CR is stand for critical. The term critical. Strain reach critical value, and here the strain reach the critical value, epsilon CR. So this is the relationship for the mill steel. For the hard steel, it will not go in the part OABCD, but it will go OAA1D1. So the curve OAA1D1 represents the relationship stress and strain of the hard steel, and steel reinforcement through cold work and heat treatment is usually of this type. And for the hard steel, we will have a greater strength of resistance. You can see here the stress the stress of the hot steel is bigger than the mild steel. But we have smaller critical strain. At the one point, we have the critical strain for the hot steel, and it's smaller than the D point. So we consider the elastic and plastic strain. When pulling steel in the elastic limits less than point A, then reduce the force. We pull the steel. The stress increase and the strain increase, and then to the point A, we reduce the force. The whole deformation is recovered, and the static curve sigma and epsilon when reducing the force back to the zero or the origin. But when we pulling steel to a certain point C, exceed the point 8, beyond the elastic limits, then reduce the force. The curve sigma and epsilon when reducing the force is a straight line CO parallel to AL, and it does not return to the origin, but still has a non-recoverable deformation path. And that is plastic strain epsilon PL. Extra strain. And the farther the point C is from point A, the bigger the epsilon PL is. Next is the strength of yielding limits, sigma y. For the mild steel, with clear yielding bed, it's easy to determine the yield limits, sigma y. And since usually the sigma y is equal to the sigma A, that's the stress of the A point. However, for the hot steel, this is for the hot steel, with unclear yielding bed, so that the sigma y is conventionally determined, and it is taken by stress when steel has the strain epsilon PL equal to 0.2%. This is the strength of yielding limits. Next one is the cold hardening of steel. Cold hardening is a phenomenon when we increase the sigma y. The sigma y is the yielding stress, yielding limits. It will increase when processing cold reinforcement. And if we take reinforcement to pull cold to exceed the yielding limits, then reducing the force will be pull cold reinforcement. This cold pulling reinforcement has a higher yield limits than the prefabricated rebar. After a few tucking or broaching, the yielding batch AB will disappear, and the reinforcement becomes harsh with the strength increase, and the critical strain will be reduced. So this is the cold hardening of steel. This one is the standard strength of steel, RSN is the standard strength of steel. The standard value of steel strength is calculated by the standard strength psi s RSN, and is taken by the yield strength, actual or conventional, with a probability of not less than 95%. So this is the formula to estimate the standard strength of steel. In this formula, the new value is the coefficient of fluctuation, and usually this value vary from 0.05 to 0.08 with good production process. And the stress sigma my is the statistical average value of the yield strength. And the compute, after we calculate the standard value, we can estimate the computing intensity of reinforcement for the limited state 1 by this formula, and for the limited state 2 by this formula. This is the computing intensity of reinforcement. Next one is the elasticity modulus of the steels. If we take the slope of the OA segment on the chart stress and strain, the value of ES is about 180,000 to 210,000 megapascal according to the steel type. That means ES is the tan alpha. The third part in this physical mechanical properties of reinforcement is the classification of group of steel. Classification of steel. According to the TCVN 1651 1985, based on mechanical properties, steel are classified into groups C1, C2, C3, and C4. And steel group C1 is the round, smooth. And from the steel group C2 to C3 and C4, we have screw, one-way screw, or bevel in two directions, or fishbone style steel. This is for Vietnamese standards. We have some group steel. And according to the Russian codes, we have the steel groups A1 for hot roll and round smooth, and A2, A3, A4, A5, A6 for hot roll, and the other AT for heat resisting steel. And this is the new standard of Vietnam. So you can see for reference the definition or the classification of steel in the new standards. And the other more reference, the steel strength is determined by pulling test according to TCVA. And here we have the standard steel strength and computing steel strength. You can see for reference later. And this the values, some physical mechanical indicators of steel in the old standards TCVN 356. Why I show you the old standards? Because nowadays some building still use the old standards, so we had to know. We had to know the old values and also the new values for current standards. There are some physical mechanical indicators of steel. The final part of the 1.6 is the physical mechanical properties of reinforced concrete structures. So at first we consider the adhesion force between concrete and reinforcement. Adhesion force is the basis factor that ensures the cooperation between reinforcement and concrete, ensuring reinforcement and concrete deformation, as well as ensuring the transmission of force back and forth between the two materials. So the factors that make up the adhesive force is due to the conjugated surface of the reinforced steels, and due to the cement glue or adhesion force, and due to the shrinkage of concrete that ties the reinforcement steels or the friction. So the intensity of adhesion force And this is the formula to estimate the maximum cohesion, and this to estimate the medium cohesion. In these two formula, N is the maximum pulling force makes reinforcement slip out of concrete, and D and L is diameter and length of steel in the concrete block. D is the diameter and L is the actual length. And omega is the coefficient completing cohesion force charge. The cooperation between concrete and reinforcement. Initial stress due to concrete screen edge. We consider concrete bar with reinforcement placed along the axis. When the concrete bar is free conduction, there will be the strain epsilon zero due to the shrinkage. But concrete adheres to the reinforcement. But the reinforcement does not have shrinkage. It hinders the conduction of concrete. So, the strain concrete due to shrinkage is epsilon 1 is smaller than epsilon 0, and relatively concrete shrinkage appears in reinforcement 1 compression force, and reinforcement prevents concrete shrinkage appears in concrete contention force, and these two forces are balanced evenly within the structure. If the tension force exerted by the steel on the concrete exceeds the tensile limit, the concrete will crack. Its cracking due to concrete shrinkage is hindered. This is the initial stress due to concrete shrinkage, and the second one is stress due to external force. We consider the simple case of reinforced concrete bar compression or tension that concrete has not cracked. Concrete and reinforcement work together and have the same strain, epsilon. So in that case, the stress in concrete is sigma b, and it's equal to the multiplication of nu epsilon and the elasticity modulus. So we can estimate the strain of the concrete. And here is the stress in the reinforcement, sigma s. And here we can estimate the NS value. And NS value is called the equivalent coefficient. And this value varies in the range of from 8 to 20. If concrete and reinforcement are both compressed, the actual force and is estimated by this formula. And if we set A dash is AB plus NS multiplied AS, it's called the equivalent cross-section area. In the concrete structure under tension or in the tensile area of the bending structure, after the concrete crack, the bearing internal force of the concrete will be transferred to the reinforcement, and the reinforcement will bear on the tension force. One another important point is the distribution. The distribution of stress due to grip. When subjected to long-term force, concrete has grip phenomena, but the reinforcement has not. The result is that the reinforcement interferes with the grip of the concrete and make the steel stress increase, but the concrete stress decrease, and is the distribution of stress due to the grip of the concrete. So the stress distribution is often useful for the cooperation between concrete and reinforcement to try to understand this phenomena. This one is the destruction and damage of reinforced concrete. The first one is the destruction due to load bearing. Concrete and reinforcement work together until failure, and with tensile bar after concrete has collapsed, the reinforcement is subject to full tension force, and it seems to begin to fail when the stress in the reinforcement reach its yield limit. So that means when the stress of the steel reach its yield limit, the tensile bar had the tension to fail. With a compressed column, the damage begins when the stress in the concrete reaches compression. And with a flexural structure, the failure can start from the area of tensile or compresses depending on the amount of reinforcement placed in the structure. So we will consider it the bending components in later chapter. That's why the damage of or destruction due to force deformation. Force deformation caused by displacement of the link due to temperature change due to shrinkage of concrete. And in superstatic structure, force deformation causes internal force to damage the concrete crack, broken, or destruction, as is the case with bearing load. And the third one is the damage caused by environmental effects. With the mechanics damage, concrete was endowed by rains or flow. And about the biology, actually bacteria will make the concrete surface crack. And regarding chemistries, concrete is endowed by acids, salts, and siltous gases due to the chemical and electrolytic effects of the environment. So this is the end of the 1.6 part of chapter 1. determine. Next, we will continue to study the part 1.7, content and steps to design reinforced concrete structures. So the steps to design reinforced concrete structure include 7 steps. The first step will be description, introduction to the structure. The second step is select the preliminary dimensions of the components. And the third step will be set up computing diagram. And for the four steps will be the determine the times of loads acting on the structure. And the fifth step will be calculate, draw internal force graph, internal force combination. And the sixth part will related to directly to our subject. In the step 6, we will calculate or estimate the reinforced concrete. Calculate the reinforced concrete. And the step 7, detailed design and expressions. So first, the general concept. Reinforced concrete structure must ensure durability, stiffness, and stability in general, as well as individual parts of the structure at all stages of construction and use. And the choice of structural solutions should stem from economical and technical rationality in specific construction conditions, taking into account the maximum reduction of materials, labor, and construction costs. Structural design of reinforced concrete includes calculations and structure. So the design includes calculation and structures. So a structure design products will be drawing and specification. Specification is the documents that explain in detail the drawing. So the design of reinforced concrete structure must ensure building durability, satisfy user, and use reasonable materials, and convenient for constructions, and low cost. So here's the flow chart for designs reinforced concrete with 7 steps. Next is the part 1.8, concept loads, internal force, and combinations. At first, we consider the loads. Loads are the force acting on the structure. When designing, loads should be determined according to the corresponding standards. For house, industrial, and civil structures need to use standard loads and impacts, TCVN 2737/1995. And here we have the classifications of loads. So based on the nature of loading effect, there are 3 types: regular loads, temporary loads, and special loads. And here are the definitions of each type load. Regular load or dead load has a constant effect during the working of the structure. For example, we have the weight of the structure itself or the fixed partitions, etc. And the regular loads or dead loads will be determined based on the structural size and the cell weight. The second type of load is the temporary load or the lead loads. The lead load is the load change in the set point, direction or magnitude, load of people and gas, or the wind loads, also a temporary loss, or loss of means of transport. And the temporary loss will be determined based on criteria through the statistics. The third type of load is the special load. They are earthquakes, fires, and explosion loss. That's the classification of loads based on the nature of loading effect. Another classification of loads is based on duration. That means the time of acting loading effect. So in this type of classification, we have long-term, short-term, and repetitive loads. The long-term loads will be including dead loads and part of lived load. Part of lived load is the long-term lived load. And the short-term loads will be the rest of the lived loads, the short-term lived load. And repetitive loads is the loads with the fast changing values and usually on parallels. For example, the vibration loading of the machine on the building. So here we have the loss and impact standards. This is the name of the loss and impact standards. And we have here is the dead loss, live loss, and special loss. And here is the long-term loss. Is the dead loss and the long-term part of the live loss. And here we have the short-term loss is the remain short-term live loss. And in the construction, we must understand the standard and computing values of loss. So the standard value of loss, that means load in standards. And usually the name of the standard value of loss will be QTC. And it's equal to the value of common in using the structures design. We have another value of loss is the computing value of the loss, QTD. And this value will be calculated based on the standards. So QTD is equal to N multiply QTC, where N is the reliability coefficient, the coefficient of overload. This coefficient will include unexpected cases. The loss exceeds the standard value, and which is disadvantage to the structure. And according to the standard TCVN, we choose N is equal to 1.1 to 1.3 for regular loss, and E is equal to 1.2 to 1.4 for temporary loss. For regular loss, when reduced loss make the structure more unfavorable, it must be taken and is smaller than 1. So here we have the standard loss is deduct calculations or look up the table. And the computing loss will be calculated or deduced from standard loss, taking into account the coefficient of overload. This is the coefficient of overload. So here are some reference you can see for yourself. In Vietnamese, in the TCVN standards. And here is the load combination. Load combination is the summation of the dead loads and other live loads with the combination coefficient. And here we have the Vietnamese load combinations formula. And here we have the load combination formula for European cost 2. And here is the American cost ACI. It's the formula for the load combination for American standards ACI. Let's consider the determine internal forces. Internal forces is in structure included bending moment, shear force Q, and axial force N, and twisting moment MT. Internal force in a structure is caused by loss or force displacement. And when determining the internal force, it is necessary to know whether the material is working in an elastic state or has plastic strain to use an appropriate calculation stream. If so, it is needed to know if the structure is static or hyperstatic. So your duty is to discriminate static and hyperstatic. Static structure use material strength or structural mechanics to determine internal forces. So you have to learn this both of this subjects before learning this subject. Before learning the reinforced concrete structure subject, you should study material strength subject and structural mechanics to understand how we can determine the internal forces. For hyperstatics, there are two diagrams. The first one is elastic diagram, and this diagram uses structural mechanics to determine internal forces. And the second diagram will be plastic diagram. In this diagram, we consider the plastic deformation of concrete and reinforcement, and only used for beams and conventional slabs. And here is how we can calculate the internal forces. So the internal forces will be the bending moment, axial force, and shear force. And this the loads acting on the beam. And here is the load combinations. And combination of the forces. And we calculate the internal force for each case of loading. Then we combine the internal forces to find out the maximum and minimum values of internal forces. And we construct or draw the internal force envelope diagrams. And we use this envelope diagrams to design the reinforced concrete structure. So here is the internal force combinations. So it is necessary to calculate and draw the internal force diagram for dead loss case and the probable case of leap loss. The combination of internal force to find its detrimental value is S. So here is the detrimental value S. And in this formula, the Sg is the internal force due to the dead load, and Sig is the internal force due to the ith case of the J leap loss. And several leap loss may be active simultaneously. That means active at the same time. So at each section, Hg is a constant value. However, as Ij is changed about values and sign. So in order to obtain unfavorable value of S, a choice must be made for Sij to take into account. And the gamma value here, gamma value is the combination coefficients. And according to the TCVI standards, load and impact standards, we have gamma is equal to 1 when checking only one leap loss. And gamma is equal to 0.9 when more than 2 leap loss are considered. Next, we will study the ninth part of the chapter 1. And this is very important part in this chapter. So let's focus on this part to understand the meaning. Computing method of reinforced concrete structures. At first, we will consider the states of stress and strain states. For example, here we have a simple beam, and these bending beams as shown in the figure, and the load Q is increased from 0 to QP. 0 to QP, increase from 0 to QP. And when the load increase considerably, there are two types of cracks in the beam. There are two types of cracks. The first type of cracks is perpendicular to the beam axis. This is the first type of crack. It's perpendicular. That means it has the angle 90 degree to the beam axis. And the latter is the oblique to the beam axis. This is the second type of crack. And first, we consider the crack that is perpendicular to the beam axis. That means this position. And following the increase of moment value, observing the stress and strain state of reinforced concrete beams, you can divide into 3 states for convenient observations. When the moment is small, that means the small loss, then the stress in concrete and reinforced is not big. Here we have the reinforcement here, the red line, and the white part is the concrete. When the stress in concrete and reinforcement is not big, the material works in elastic phase and the relationship between stress and strain is linear. You can see it's a straight line. And the neutral axis, this is the neutral axis. Neutral axis is the zero stress axis. And this axis is almost in the middle of the beam. And we call this state is the state number 1. And when we increase the load, the moment is increased. And in the tensile concrete area, this is the tensile concrete area, there appear lattice strain. So you can see here the chart is not a straight line, but will become a curved line. It has a nonlinear relationship here. And when the tensile stress in concrete reach the tensile strength of concrete, RBT. Here, the tensile stress of concrete is smaller than the tensile strength of concrete. However, here, the tensile stress of concrete is equal to the tensile strength of concrete, then the area of tensile concrete prepares to appear crack, and we call this state is 1A. As the moment continues to increase, the tensile stress in concrete this sigma BT is the tensile stress in concrete. It's bigger than RBT. RBT is the tensile strength of concrete. Then in the area of tensile concrete, the cracks appear and also develop upwards. And as the cracks, internal force is carried by reinforcement. when the concrete cracks, it doesn't work. So the reinforcement will carry on the tensile stress here. And in the tensile concrete region, this is the tensile concrete region, the plastic chain continues to grow while the stress in the tensile reinforcement is smaller than the tensile strength of the reinforcement. Sigma S is the tensile stress of the steel or the reinforcement, and RS is the strength of the steels. And the stress of compressed concrete is smaller than the compressed strength of concrete. So this case is the state number 2. So from this state 2, if we increase the moment, and based on the amount of reinforcement, it's not much or it's much, we divide it into 2 branches. The first branch is if the amount of reinforcement is not much, when the moment is increased, the stress in the reinforcement may reach the zero limit. That means the stress of reinforcement, sigma S, is equal to the zero limit. That means it's equal to the reinforcement strength. While the compressive stress of concrete is still smaller, you can see here the compressive stress of concrete is still smaller than the compressive strength of concrete. So we call this stage is the stage 2A. As the moment continues to increase, the cracks continue to grow upwards. And the compressive concrete region continue to narrow. You can see here X is the compressive concrete region height, and this region is narrower. And the compressive stress of concrete increase while the tensile stress in reinforcement still equal to the tensile strength of the reinforcement. Because reinforcement is in yielding phase, when the stress in compressive strength reach the compressive then the beam is damaged, and damage in both in tension and compressions. And we call this the plastic damage case or the first damage case. And this the first damage case. And this the most logical damage case because it has full advantages of the bearing capacity of concrete and reinforcement. This is the most logical damage. So another branch will be if the tensile reinforcement is applied too much. That means we put or we arrange reinforcement here. So much reinforcement here. The tensile stress in the reinforcement is always smaller than the tensile strength of the reinforcements. That means the stress always smaller and never reach the value of the strength of the steel here. While the compressive zone has been damaged in advance, the beam has been damaged, and there is no stage 2A. In this case, there is no stage 2A. And this phenomenon is called brittle failure. and sudden destruction from the area of compressed concrete, and also known as the second failure. And this case does not make full use of the bearing capacity for the reinforcement because the stress never reach the value of the strength here. So it's also very dangerous because at that time the strength of the beam is still small and it's difficult to prevent. So in summary, we have the stage 1, then we increase the loss. It will develop into the stage 1A, then develop to the stage 2. And from the stage 2, if you arrange reinforcement not much, it will go to this branch, go to stage 2A, and then go to the stage 3 limited stage 1. However, if we arrange reinforcement much, then it will go to the second branch and go directly to the stage 3 limited stage 2. So be careful when we calculate and arrange the reinforcement here. Next is the method of calculating reinforced concrete components according to the limited stage. So limited stage with the abbreviation is LS. LS is a stage in which the structure no longer satisfies the requirements of its use when designing. Consider the reinforced concrete material is elastoplastic material, and taking case 1, phase 3 of the stretch and strain stage as a basis for calculation. So for the limited stage 1, we calculate according to the durability to ensure the structure is capable of load bearing during use, and no brittle plastics or other damage, no loss of shape or position instability, and not due fatigue. For the limited stage 2, we calculate by deformation to ensure normal working for the structure during use, and there is no strain that exceeds the permissible limits, and we do not allow the formation and expansion of cracks beyond the allowable limits. So here we have many calculation methods. For example, allowable stress design. And for allowable stress design, this is the linear elasticity analysis for internal force calculations. And reinforced concrete is considered as an elastic material. And this model is only used a safety factor for the whole structure. Another method is the limit stage. And this method, we have the linear elasticity analysis for internal force calculations. And reinforced concrete is elastoplastic material. And it's quite different from the allowable stress design. It's only elastic material, but here we have the material of reinforced concrete is elastoplastic. We consider both the plastic strain in calculating reinforced concrete structure, and we use many reliability coefficients or safety factor for loads and materials. So for the limited stage 1, calculate reinforced concrete, we calculate and check the durability, and we ensure do not suffer from computational force that cause little blood or destruction. No instability in shape. For example, instability in shape of thin wall structure, or no instability in position. For example, sliding, flipping, or pushing, and no fatal damage under dynamic load, or not being damaged by the environment. For example, erosion or fire. For the limited stage 2, we calculate reinforced concrete and we calculate and check crack and deformation. And we ensure no excesses allow deformation, for example, deflection, rotation angle, sliding angle, or oscillations. And we do not allow the formation of cracks, and structure does not crack or expand beyond the permissible level. Structure allow cracking. So this, the width of the cracks is smaller than allowable value, and this the length of the crack is smaller than the allowable value. So here are some reference in Vietnamese you can look for reference. Finally, we go to the 1.10 part of chapter 1, principle of basic composition of reinforced concrete structures based on the Vietnam standards TCVN 5574 2018. And in this 10 part, we will have choose the side to the section side and reinforced frame and grids, connecting and entering reinforcement, concrete layer protest reinforcement, and minimum spacing between reinforcement bars. The first one is choose the section side. So the section side is usually preliminary selected to determine the load internal force, and from which the reinforcement is calculated. Then we need to calculate the percentage of reinforcement or the content of reinforcement. V is the content of the reinforcement. It's equal to the division of AS. AS is the reinforcement area, and A is the total cross-section area. And we calculate the mu value, that means the content of reinforcement, in order to evaluate the rationality of a section. And if it is not reasonable, the section must be selected again. Choosing the side of selection, in addition to the requirement for bearing capacity, must also pay attention to aesthetics and construction condition. Usually choose the thickness of the board and the wall in multiples of 10 or 20 millimeters. For the girdle cross-section, we choose the section size in the multiples of 20, 50, or 100 millimeters. And this is how the reinforcement are linked together. Reinforcement is placed in concrete in the form of frames or grid. And this is the frame. And this is the grid. Frame format will be used for beams and columns. For example, tie frame or welding frame. And this the grid form of reinforcement. This form of the reinforcement will be often used by in the slab with tie grids and welding grids. And here we have the steel frame with the main steel and shear up steel. Conducting and entering reinforcement. Connecting reinforcement. We have many types of connection of the reinforcement. The first one is the welding connection. Welding confrontation or welding stacking. The second one is the fasten connection. We place the two ends of reinforcement. A segment LAN is the actual length. LAN is the actual length. And we use soft steel wire. Here we have soft steel wire. The black part, soft steel wire to tie. So we have to pay attention to the quality of reinforced concrete areas in the connection. And we have to calculate the actual length. LAN. So in this formula, we have omega AN, delta AN, and lambda AN are the table lookup coefficients. And D is the reinforcement diameter. Reinforcement diameter. RS the computing strength of the reinforcement. And RB is the computing strength of concrete. And gamma B. Gamma B is the working condition coefficient of concrete. Here we have the axial reinforcement. To fully utilize the building capacity of reinforcement steel, its ends need to be firmly anchored to the concrete. For example, here we have the reinforcement of beam will be anchored firmly into the column. And here we have the reinforcement of the column will be anchored into the beam. For smooth round bars used in frames and nets, it's required to bend the hooks at both ends. Here, for the smooth and round bars, it's required to bend the hook. This is the hook. Bend the hook at the ends. And this formula is similar to here. And those coefficients are looked up from this table. Next, the concrete layer protects reinforcement and minimum spacing between reinforcement bars. Concrete layer protects reinforcement A0 is necessary to ensure the simultaneous operation of reinforcement and concrete as on stages of the structural works, as well as to protect the reinforcement from the effects of air, temperature, and other impacts. And the reinforcement is placed with a gap T wide enough to allow the concrete mortar to easily pass through and to give each reinforcement bar a sufficient layer of concrete to ensure adhesion. So according to the Vietnamese standard TCVN 557 for 2018, this standard specifies that the clearance T should be greater than or equal to the maximum reinforcement diameter and the value of T0, so in the following figure. So here we have the concrete layer protects reinforcement A0. A0 is the concrete layer protects reinforcement. And in any cases, A0 must not be smaller than the corresponding reinforcement diameter. So A0 must be bigger than the diameter of this reinforcement and must not be smaller than the value 0 is prescribed as follows. So with building load reinforcement, we have many values of 0 and the A0 must be bigger than C0 and the diameters. And here's the clearance between reinforced bar. The T value is the clearance. Must be, for example, for the upper layer of reinforcement in beam, we have the T values must be bigger than 30 millimeters and the diameter, the reinforcement diameter. And for the lower layer of the reinforcement in the beam, we have the T value must be bigger than 30 and the diameter. And here is T is bigger than 25 and D. Also here, T is bigger than 25 and D. And this for the column. The other slide is the reference, so you can this for yourself. Here are some reference of the principle of basic components of reinforcement. Here some reference. So this is the end of the chapter 1. At the conclusion of this lecture, students are required know the course requirements. So after learning the chapter 1, you must know the course requirements and know to find and study knowledge and important information source related to the lecture. And you can describe the behavior of the reinforced concrete structure. And you are required to discriminate the physical-mechanical properties of concrete, steel, and reinforced concrete. And you are required to state the steps to design reinforced concrete structure. That means the 7 steps. And which step is related to our subject? You must be understand. And you can combine the loads and internal force combinations. And can propose the calculation plan and basic composition of reinforced concrete structure. And this part related to the part 1.10. So in the later chapter, you will learn the members in bending. And remember to do your homework number 1 and submit it online. In the homework number 1, you will have the 2 questions. The first one is why concrete and steel can work together in the reinforced concrete structure. So in order to answer the first question, you have to read the lecture of chapter 1. And the second question is describe the behavior of concrete and steel in the reinforcement concrete material. So this is the end of the chapter 1. Thank you for your attention.
Tại vì một số bạn là khả năng là rút môn học, nên là nếu mà tuần sau mà môn học mà vẫn còn đủ số lượng sinh viên thì chúng ta sẽ tiếp tục. Hôm nay cảm ơn các bạn đã online. Các bạn có thể nghỉ nha.